So, welcome back student to the next class of nonlinear optics and in the application. So, today we will going to learn a very important topic in nonlinear optics, which is Raman scattering, and then gradually we learn the Raman amplification and stimulated Raman scattering, etc. So, what is Raman scattering? So, let us give you a very rough idea about that. So, we know that in Rayleigh scattering what happened in if some light wave is coming or the photon is coming to the material. So, the atoms can go to ground state to some virtual state and then return back to the ground state, and we will have a similar when it go to the ground state it emits, and if it is some sort of elastic kind of scattering, then we will going to have the same wavelength. So, there is no change of wavelength. So, this is a simple Rayleigh scattering kind of phenomena, where due to some elastic scattering process there is no change of wavelength or frequency. On the other hand, in Raman scattering process, if you launch a photon, if the photon is interacting with the material, then whatever after interaction whatever is coming out is may not be the same wavelength that is launched to the system. So, the wavelength may be greater than to the launched wavelength or the less than to the launched wavelength, depending on the system. And here, since the energy is exchanged, so the energy conservation, obviously the energy conservation should be there, but input and output wavelength or frequency is not same. What happened here? So, the molecule can go from ground state to some virtual state and return back to some final state. This final state may not be the ground state. So, there is a difference between the energy from ground state and final state. So, the ground state the molecule have one vibrational state or rotational state. When it absorbs some kind of energy from the input wave, what happened that it will start vibrating or rotating some frequencies. So, the molecular vibration or rotational state is now changed. So, this is now in higher energy state. Since it is absorbing some sort of energy, whatever is coming out from the system should be less than of the energy that is launched to the system. So, obviously, the amount of energy difference delta E is nothing but h cross omega p minus omega s. Now, if omega p minus omega s is delta omega, so delta omega is the frequency at which this molecule is vibrating or rotating. So, this is the corresponding frequency. In a similar way, if the molecule is already in some excited state and then some energy is falling. So, this molecule can go to some virtual state and then go back to the ground state, where in the ground state it can lose some kind of energy, and we will have some amount of added energy here, and the wave that is coming out from the system or the material is more than whatever is launched. So, here omega A s is greater than omega p. So, we have a wave, we have a frequency which is greater. Here omega s was less than omega p. So, two different procedure, different system can be possible. In one case it is called Stokes system, and in another case it is called anti-Stokes system. So, we all are aware of these two processes. So, today we will going to learn in detail exactly what is going on in Raman scattering process in terms of nonlinear optics. So, before going to these things, there are few notation that we need to understand, that is the generalized coordinate. So, in classical theory of Raman scattering, what happens? So, this is the left hand side of this process, and the left hand side of this slide gives the process of the classical Raman scattering. So, the classical treatment suggests that a monochromatic wave which is E0 cos omega p t, omega p is the frequency of that monochromatic wave, it is launched to the system, and as a result what happened, that the molecule is the molecule is now vibrating with that particular frequency, and microscopic polarization can generate. Because of this vibration, the average position of the molecule can change, and since there is a charge separation, we can have a charge separation multiplied by the distance, and this charge separation multiplied by distance can give rise to some microscopic polarization. So, this microscopic polarization can be represented in this way. E1 is a field that is launched, epsilon 0 is as usual there, and this alpha basically called microscopic susceptibility. If you look carefully, the form is exactly whatever the form we use normally. So, it is used like this way, chi 1 this is the normal way to write the polarization. Here we are writing the same thing, but we write microscopic polarization because this susceptibility thing is only for this particular molecule. For the timing, later consider that. Now, this microscopic susceptibility is a function of generalized coordinate. That means, the molecules are vibrating. Since this is vibrating, its generalized coordinate is changing. So, we consider that since the generalized coordinate is changing, this is a weak function of this generalized coordinate q. So, alpha is a function of q. If it is a weak function of q, we know that any function can be expanded in terms of Taylor series. So, if I expand this as a Taylor series, we have a first order term and a second order correction term, and since it is the function of q, it should be the derivative of that quantity multiplied by q. If I go to higher and higher order, it should be the double derivative of alpha with respect to q at central point, which is 0, and then q square with a half term and so on. So, it is simply a Taylor series, but since we say that this is a weak function of q, so q square, q cube and all this term we are not going to consider. So, this is the microscopic susceptibility, and now microscopic susceptibility is written explicitly in terms of q. Now, what is q? Let us try to understand very quickly what is generalized coordinate. So, generalized coordinate is something where, say, this is the molecule and this molecule is sitting in some coordinate system, one dimensional coordinate system. So, this point I can write x 2, this point I can write x 1. Now, if it is stretched, this position is changing. So, now x 2 become x 2 prime, x 1 become x 1 prime. So, now the change of length is x 2 prime minus x 1 prime minus of x 2 minus x 1. That means, this length minus this length, as simple as that. So, if I do, then I can readily find that this difference is nothing but this quantity whatever we have, if it is q 1 and this q 2 is related to these two parameter. So, q 1 and q 2 if I combine, I will have a one coordinate q. So, all this coordinate can be combined in such a way that I can write a simple generalized coordinate to understand the dynamics of this system. Here q is a generalized coordinate. So, this q is a function, this microscopic susceptibility is a function of q. So, since microscopic susceptibility is a function of q, I can expand this in this way. Well, next, same system, monochromatic field is launched, and because of this monochromatic field, the molecules are now vibrating. So, since the molecule are vibrating, so it may have some generalized coordinate which can give the idea how this position of this molecule is going to change, etc. So, if it is a sinusoidal field, then we can write q as a sinusoidal also, but note that I write a different frequency. It is may not be the same frequency the way molecules are vibrating, and it is quite obvious that molecule, because of this monochromatic field radiation, the molecule can go from lower energy to higher energy and return back to some final state and then start vibrating to that final state. So, omega is the vibration of or the frequency of this final state I am talking about. So, P is a microscopic polarizability. Microscopic polarizability can be now expanded in terms of Q, because alpha is a weak function of Q. So, alpha is alpha 0 plus d alpha dq at 0 point multiplied by Q, and EI is electric field. Now, EI is E0 cos omega pt. I just simply write this quantity and then I multiply these things to and make it two different terms. One term is epsilon 0 alpha 0, both are constant, E0 is constant and cos omega pt. That means microscopic polarizability is now vibrating with one frequency, which is omega pt. But other term is still here, which is multiplied by Q and E0 cos omega pt. Q is vibrating with this frequency, so it is important because we need to take care of that also. So, now the polarizability has few frequency terms. Epsilon 0 alpha 0 E0 cos of omega pt, usual term already there. Next term is Q multiplied by EI. EI is E0 cos omega pt, and Q is also, so we know that Q, we have already represented this Q as cos of omega t. So, I write explicitly Q as Q0 cos of omega t. So, now if I simply manipulate this term cos omega t and cos omega pt, cos big omega t rather cos omega pt, then if I take a half term, then half of cos omega t into cos omega pt can be represented as cos of omega big omega plus omega pt and cos of big omega minus omega p of t. So, now you can see quite easily that this microscopic polarizability is having three different frequency components: original frequency and two other frequencies here and here. And here if I write in terms of frequency, the microscopic polarizability is now having three frequency component: original frequency plus big omega, which is the vibration of the molecule, and original frequency minus omega, which is, that means some sort of energy that is reduced from the original frequency. So, microscopic polarizability is a source of field, microscopic field. So, one microscopic field can generate due to this term, which should have a frequency omega p. One field can be generated due to this source term, whose frequency can be omega plus omega p, and another field can still be generated and whose frequency is omega p minus omega. Mind it is a cos, so it does not make any difference if I write cos of omega p minus omega, because cos of omega minus omega p is same as cos of omega p minus omega. Since omega p is much greater than omega, it is better to write this notation, but anyway, since it is a cos, so there should not be any difference. Well, if I now try to understand that exactly what is going on, and this is a pictorial figure for that as I mentioned, this microscopic polarizability now vibrating in three different frequencies. So, these three different frequencies give rise to three different waves, and these three different waves, if I write in the output, if I try to find out what is the spectrum of these three different wave, I will find apart from this central frequency, if I write this pump frequency as central frequency, one frequency will be more than central frequency, which is a anti-Stokes wave, and another frequency will be less than omega p, which is some sort of Stokes waves. So, this microscopic polarizability, because microscopic susceptibility is a function of generalized coordinate. Generalized coordinate is vibrating with some frequency. Generalized coordinate is related to the coordinate of the molecule. So, try to understand once more what is happening here. One electric field is launched. Because of this electric field, what happened? The molecules here is now vibrating. This vibration of the molecule can be represented with a frequency, say omega. The launched electric field has a frequency omega p. Because of this nonlinear, because of this polarization, microscopic polarization, we have a microscopic susceptibility. So, this microscopic susceptibility is a function of q. When they multiply with the input field, then we have the interaction of the molecule and field. This interaction of the molecule and field give rise to two different frequencies. One is omega p plus omega, which is higher than the launched wave or launched frequency. We call this anti-Stokes, and another is Stokes, which is less than the frequency that is launched. So, two different frequencies can be generated, and this is happening because the electric field is directly interacting with the molecule. So, the light matter interaction is directly here, and because of this light matter interaction, we are getting the frequency which is higher and lower than the frequency here of the launched frequency. So, after having a very simple straightforward thing, now we try to understand stimulated Raman scattering. So, what is stimulated Raman scattering? So, we already find that if omega p is launched, so there is a possibility that omega p plus something and omega p minus something can be generated. So, let us try to understand, if I generate say anti-Stokes, that means omega p minus something, if I write it is omega s. So, how this omega s can be amplified? So, in order to amplify this omega s, what happened? I launched omega p to the system. This system I have say chi 3 not equal to 0. Then along with omega p, I also launch omega s. In the output we have omega p and also omega s, but omega s is amplified. You can see it is amplified. It was a weak wave, but there is an amplification. So, what is the process here? So, our treatment will be exactly the same. EP, the field with omega p frequency can be represented in this way: EP to the power I k p z minus omega p t. The field associated with the Stokes waves or the Stokes frequency can be represented at E s e to the power k z minus omega t, omega s t plus complex conjugate. Total field is E of omega p plus E of omega s. Microscopic polarizability P is epsilon 0 microscopic susceptibility multiplied by the total electric field E, and here we consider the total polarization. So, when we consider the total polarization, we make an approximation and we multiply the P with the number of molecule per unit volume n, or the number of dipole per unit volume n. So, multiplying n, we have the total polarization. So, microscopic polarization can be represented in terms of total polarization, but microscopic susceptibility is still a function of q, which is the most important thing here in classical treatment, and I can write this explicit form of alpha, which is a function of q. So, all the things are now in our hand, and try to understand how the stimulated process can be generated. So, EPES is in our hand. Microscopic polarizability can be represented in terms of total polarizability. So, total polarizability is now in terms of microscopic susceptibility, Microscopic susceptibility is represented in terms of Q. So, Q should also be in our hand. So, now see what happened when you try to calculate the stimulated Raman process. So, as I mentioned, P is n alpha epsilon 0 and E. Alpha is a function of Q. So, I can write alpha in this way. Alpha is a function of Q, weak function of Q rather. So, I write alpha 0 plus d of alpha dq at 0 point multiplied by Q. So, this is the thing. So, total P is this quantity plus this. So, now I divide the total P into two parts. This is a linear part and this is a non-linear part. So far in the we know that total polarization can be represented in terms of P linear plus P non-linear. P linear we know how to represent, it is chi 0 epsilon 0 chi 1 E, and P non-linear, if second order effect is there, then it should be epsilon 0 chi 2 E square. If third order effect is there, it is epsilon 0 chi 3 E cube. This is the way we represent P non-linear. So, here since chi 2 chi 3 is not directly, it is not coming here because we are dealing with microscopic susceptibility. So, we simply write this into two parts, one is this which is a linear part and another is this which is a non-linear part. So, non-linear part is now in our hand, and in non-linear part we have n epsilon 0 d alpha dq 0, all these things are constant, multiplied by Q and E. Mind it, U is a total field. So, U should be omega p plus E omega s. Fine. Next, we need to find out what is the differential equation for the molecule. So, when the electric field is launched, what happened? The molecule goes from ground state to virtual state and return back to some final state with a vibration, and this vibration should have frequency delta omega, which is the difference between omega p and omega s. So, energy conservation is totally valid here. So, since this energy conservation is valid, we can write that this molecule is now vibrating with a frequency delta omega. Now, we try to understand the dynamics of this vibration, because our aim here is to find out this Q. Our aim here is to find out the form of this generalized coordinate. In order to find out this generalized coordinate, so I need to write the equation of motion and solve it. So, the equation of motion is for this molecule which is vibrating as a frequency delta omega is simply a force damped oscillator model, because I am launching some electric field which is, because of that it is vibrating, and when it is vibrating it should have some sort of resonance frequency and some sort of damping. So, m multiplied by, so normally this equation is m x dot double dot plus gamma x dot plus say omega square m gamma x dot multiplied by m omega r x is equal to some force term. So, we have been using this equation, I mean we have used this equation in earlier classes. So, we are using the same equation here, but instead of x we are using the generalized coordinate, because here everything is represented in terms of generalized coordinate. So, now if I try to understand what is the equation. So, this equation is simply force damped oscillation, and this force damped oscillation model if I use for this particular molecule, this equation is simply comes out to be this. Force is something that we need to calculate here. So, what should be the force on these things? It is nothing but d dot E. So, if a electric field is launched, so some kind of potential energy that is stored here. So, this potential energy that is stored in the system is nothing but d dot E with a half term and a negative sign, since it is stored, which is half epsilon 0, half epsilon E square, because d is epsilon E. So, if I put it here, and if d and E is in the same direction for isotropic system say, so it will be minus of half epsilon 0 E square. So, now we know what is my potential, which should be a function of q, by the way. So, this potential term, now if I make a derivative of this potential term, then only we can find out the force term in our hand, which is important. So, we need to know what is the force experienced by the system. Well, how to find out this? So, in this slide we will going to understand. So, total D is epsilon 0 E p, we know. P here is the polarization, we know this polarization can be represented in this way, epsilon 0 n alpha E, because alpha is a microscopic polarization. Everything so far we are doing is in terms of microscopic polarization. So, D is epsilon 0 1 plus n alpha E, and this is epsilon E. So, epsilon I can extract from this equation, and epsilon is 1 plus n alpha q epsilon 0. Alpha q is something which we know, because this is an explicit function or the expansion that we are using. So, alpha q we are using that, it is not, this is alpha 0 plus d alpha dq and then q. So, once we have these, we put this here. So, V is now written completely in terms of q. So, V is a function of q. So, q was inside this epsilon. So, I now expand this epsilon. So, when I expand this epsilon, V is now represented in terms of q. So, once we write, it is epsilon 0 E square. So, F is the derivative term, because F was the grad of this thing. So, only one variable is here q. So, it should be minus of del q and V of q. So, now if I make a derivative, it should be simply half epsilon 0 n this quantity and E square, because this E will, because of derivative, this term will be affected, other two terms will going to vanish. So, F is calculated. So, once F is calculated, we can have Fm, which is the force per molecule. The force per molecule, we just simply divide the total number of molecule per unit volume, which is n, and finally we have Fm in this form. So, once we have Fm in our hand, then the differential equation can be a little bit simpler, because in the right hand side we know everything in terms of electric field and alpha, which is which is the information that we have so far. So, in the right hand side we can see, so this is the total equation, the equation of molecule that is vibrating as a frequency delta omega, as I mentioned. So, this equation is now having a compact form. So, today we will not going to solve this equation, because it will take some time again to solve this equation. It is easy, but it will take some time to solve. But important thing is that in the right hand side, the total field is, in the right hand side, the force is written in terms of the external or the total field E and the corresponding alpha value. Directly alpha is not involved here, but the derivative of alpha is here. So, in the next class we will start from this part. So, we have derived so far that if I launch an electric field, the molecule will be excited and vibrating in some frequencies. If it is vibrating some kind of frequencies, then the important thing that what should be the generalized coordinate, because the generalized coordinate is important to know what should be the nonlinear polarization associated with that molecule which is vibrating with certain frequencies. So, first we need to solve the differential equation of the vibration of this molecule. So, then we use the damped force oscillation model here and first find out what is the corresponding field and what is the corresponding force in terms of field that is experienced by the molecule, and we have derived a differential equation. So, next day we will going to solve this differential equation and find out what is the generalized coordinate q. Once we know the q, next we find out what is the corresponding polarization. So, polarization, nonlinear polarization value explicitly we can know once we solve this equation. So, with this note, so let me conclude here. So, thank you for your attention and see you in the next class.